So now let's look at the shifts in separate instances here. Okay, so now we said that one of the shifts is called vertical shift. Okay, then we said the other is horizontal shift. So we're looking at shifts first. So now, what happens with the shift? So when you look at the equation they give you, or the expression, the function they give you, say for example it's y is equal to x squared, right? So it will not always be given in that format. Sometimes they may give it to you in x squared plus 3x plus 2, maybe something like that. So what movements are these going to be? So we said that the original format of the equation will be something like that, or the function will be something like this. But if we make changes to this, okay, it can either move this this way or that way. Okay, so now let's look at what makes these movements. So if you had a situation, so we're considering the vertical shift first. So if you had a situation where you have y is equal to fx is what? It's this, plus c. Notice this is outside there, maybe plus 2. This will cause a vertical shift. Okay? What is a vertical shift? It's movement along the y-axis. So this will move this way. Because I've said what? I've said plus c. Take note of that. What happens if I have this same equation, same function, and I say minus c? Take note of the minus. This will move c units down, but will maintain the same shape. So it'll be same side. So this is minus c, that is plus c, and this is the origin. Okay, so this is what this does. So you can have x squared, it'll be this one. Then this will move it plus c units up or down. So this is plus c units, we'll take it up. This is going to be x squared plus c. Then this is going to be x squared minus c. Okay, so these are like this. Maybe plus 2, maybe x squared minus 2, right? So these are the movements that this will make. Okay, so now we look at horizontal shift. So now what function do we have here? We still have the same one, fx. Okay, that's the parent form, which is what we're using. X squared can be any function. Okay, now if we come and we say this is going to be x plus c, notice that this is not outside here, like it's different from this. Now I'm changing the value inside here. Okay, so if I've changed the value inside here, it means that I've reduced the strength of this one here. So it means that if I add, for me to maintain the same value here, it means that I've reduced the power of this one. You can actually equate this to 0, just to make it easy for you to remember. Then this will be minus c units, right? So minus c units. So if I add something here, I've reduced the value of this one. Okay, that's how I think about it. Then this moves c units along the horizontal plane. Okay, and then if I were to say y is equal to fx minus c, okay, for me to maintain this, it means that this has grown, meaning that if I did something like this, I will have something like that plus C. So meaning that if I take away, I'm going to have to move this positive C units on the horizontal plane. Okay, so now we can see that we have two things that are happening. We can move it up and down or across, but something is very strange when it comes to the shift. When you add a unit, it actually moves it left. When you remove a unit, it actually moves it right. So this is something to remember. Everything is normal on the vertical shift. Adding moves it up, removing brings it down. But here, there's an opposite here. So if I take away, it moves in the positive direction. If I add, it moves in the negative direction. So key thing to remember. Another concept is reflection. So we can reflect on the x-axis or we can reflect on the y-axis, right? So on the x-axis, it'll be, this is our, look, this can be anything, can be a straight line, can be whatever, but we just need to know that it's reflecting on which axis. So here, this is the quadratic. We said it's x squared. So what do I need to do to reflect it on the x-axis? I just need to introduce a negative sign. So this becomes y is equal to negative fx. So whatever the function was, if I negate it, then that becomes, in this case, it will be y is equal to negative x squared, like that. So if it's on the, this will reflect it on the x-axis. Remember, this is negating the whole function, right? Now, we can go and look at functions that can be reflected off the y-axis. I can't come and reflect this on the x-axis, on the y-axis. It will be the same thing repeating. So if I come here and I get a function like this, all right, so this is this function, right? So if I were to reflect it off the y-axis, okay, what will it become? So this gets reflected there. Let's use a different color. So this gets reflected there, and that gets reflected there. So it's like this same graph now makes this shape here. Okay, so that is reflection on the y-axis. So what happens for something to be reflected on the y-axis? You need to say that this now was a function like this. Okay, but if I came and not negated the whole function, but just this variable inside there, so that's the difference. There's inside here, and then this one is outside the function. So this reflects over the y-axis, and if it's outside here, it reflects over the x-axis. So this has been reflected here, that has been reflected there, that has been reflected here. Okay, so let's look at vertical stretching and compression. So we can compress a graph vertically, okay, or we can compress it or stretch it horizontally. So now here we have, let's say we have a graph again. Let's say we have a graph like this. Right. So what can we do with this graph? So if I were to set my boundaries to be there, I want to maintain these because what I'm doing is I'm only moving it up and down. So this is vertical. It can only be pulled upwards or it can be pulled downwards, but it can't change in terms of these limits. Okay. So now if I were to compress this graph, okay, it will come to be something like this. Okay, so that is what we call what? We call that vertical compression, right? Then the stretching will be the opposite of this. Same boundaries, but I just take this up a bit like that. But same origin, the origin remains, and the boundaries are still maintained. So what happens now here? What happens is, this is when you add a factor, okay, in front of the function. So this is the function is equal to x squared. But if I came and say this is now 2x squared, then this is going to change this function by stretching it, okay? So they say that this one, the stretch, the c, which is the factor, c has to be greater than 1. Okay, that is stretch for vertical direction. Okay, and then for compression, how do we compress it? C has to be between 0 and 1, like that. So this will give us compression and stretching. So less than 1 means that maybe, for example, if I've got f of x is equal to x squared. If I change this function to y is equal to 2x squared, then I'm going to stretch this graph by a factor of 2. So if this was, let's say, this is not a good example, but if I had something like this, okay, then I've got my function, my first function as this, maybe it's ending here at 2. Then if I were to stretch it, the new function will be at 4 there, like that. Okay. Then the compression is when fx, let's say it's still x squared, then I come, I say y is equal to half x squared. So this will compress it to half the, so for example, this one will come here and become a, the y value here becomes 1. Okay, like that. So this is compression, this is stretching, but in these directions. Remember, the important thing is to make sure that your margins are maintained. So it's different if I were to come and have a function like this. Okay, I've got something like that. Then my parent function is like this. Okay, then I come now and compress this to this function here. I can't do that unless if they gave me, they indicated that the domain or the range has to be maintained, or the domain has to be maintained. So for example, if they say the domain will be here, the range will be there, sorry, this is the range. So the range will be maintained here. But here there's no limitation, so you still need to come to the same domain, which is what your x value is here. So you maintain the domain. They haven't changed the domain. They haven't said that the new domain will be here. Okay. So this is vertical stretching and compression. Horizontal stretch and compression. So if I had my parent function like this, then it came like that. So you remember that this is fx is equal to x3, right? So what happens here? What happens here is that we are doing this horizontally, so we need to maintain our range here. Okay, we need to maintain our range like that. So we maintain our range. Now, what happens here? What happens is that if I were to compress this, it means that I'll bring it here inside, and I'll bring it here, there. What happens if I were to stretch it? it means that I have to bring it here and I have to bring it there. Now this is similar to horizontal shift, where we say that a factor of -3 will move it right, and a factor of +c will move it left. Okay, so what happens here is that if I had my function, which is x squared, okay, fx, like that. So if I came and say that now my fx, my new y, is going to be fx to, let's put a factor of c, cx. That now will either stretch the graph or it will compress the graph. But what are the characteristics of this c that will cause these different movements? So when c, and take note of this, when c is greater than 1, we have compression. Okay, so we have compression when c is greater than 1, almost like the similar thing to horizontal shift. Okay, it's the opposite of what you would intuitively think about. Then what happens when it's a stretch? Okay, what happens when it's a stretch? A stretch offers you this. C has to be between these values, meaning that if you know a value that's going to be here, it means that it's going to be a proper fraction. So something like 1/5 or 3/4. If you see a fraction like that in front of this x, then you know that you're actually stretching a graph by that fact. Okay.